if you have any questions, please pipe up or let me know at some point. Let's go ahead and share. Okay, so what I'm going to do today is focus. Now, there's a lot here that I'm glossing over in terms of Bessel functions because of the time that we have. But I think the things that are most important here are how the Bessel functions are solutions to some of your favorite partial differential equations in cylindrical and even in spherical geometry, and what we can do with that. Oftentimes, the functions themselves are too complicated to have a really good intuitive feel for them. What's really important is where do they become zero, and we'll look at an example, and then you'll do an example in your group. So the first thing before we get there, in order to sort of motivate this, is I want to go back to how we represent the Bessel functions. And in this case, we can look at integral representations. Okay, so we've looked at two ways to discuss Bessel functions. One is Bessel's differential equation, and we can find solutions for that. The other is the generating function, and your first problem in chapter 14 deals with how you can kind of use that generating function to get back the differential equation. But now we want to look at what else we can do, especially with these recursion relations. And in your book also has some things about summation formula and some of the other. There aren't any problems assigned with it, but there is some reading associated with orthonormalization of these functions and so on. I'm not going to cover that in our lecture. So what we're going to do instead is look at, say, the function t is equal to e to the I theta. The reason why is that we can go back to our generating function, e to the xt times e, and I'll write it a bit differently, t minus 1 to the t minus 1. That's just those two different pieces. So that we can write this as e to the x over 2 times e to the I theta minus e to the minus I theta, which just seems like it's even more trouble than it's worth. But because these can represent cosines and sines, we can write this as e to the x over 2 times 2I sine theta over 2, or e to the ix sine theta. Which is interesting in its own right, if not horrifying. But we can relate this to the different Bessel functions themselves. And I can go through some of this. So for example, we could write J1 of x times e to the I theta plus J minus 1 of x e to the minus I theta is equal to J1 of x times e to the I theta minus e to the minus I theta, or 2I J1 of x times sine of theta. And we could write J2 of x e to the 2I theta plus J minus 2 of x times e to the minus 2I theta. You can sort of see where I'm going here. This is equal to 2 times J sub 2 cosine of 2 theta. So we can write that e to the ix sine theta is equal to J naught of x plus 2 times j2 of x cosine 2 theta plus j4 of x cosine 4 theta, and so on, plus an imaginary part, plus 2I theta, that includes the odd terms. So j1 times cosine of theta plus j3 of cosine 3 theta. And so what we end up with is expressions which actually do appear in things like diffraction problems for, say, cosine of x sine of x, which you can write as j naught of x plus this sum, 2 times the sum of n equals 1 to infinity of the even terms. And sine of x sine theta is equal to just 2 times the sum from n equals 1 to infinity of the odd terms. Oops. D2. All right, so what does this get us? Well, it gets us a way of relating the Bessel functions to trig functions. And if you use some of the orthonormal properties that the book discusses, you can simplify this pretty substantially. I'm just going to cut to the chase. So see 10.2 through 10.3, for example. You can write something like j naught of x as 1 over 2 pi times the integral from 0 to 2 pi of e to the ix sine theta d theta. And you can also write that as 1 over 2 pi times the integral from 0 to 2 pi of e to the ix cosine theta d theta. Okay, so the point of all of this was to get us to a point where we can find a solution for these seemingly improbable intervals. These intervals are starting to look like, if you haven't seen them already, Fourier transforms. And Fourier transforms, if you have seen them, you know that they play a big part in optics as well as quantum. So the example I want to use, certainly to go over, is basically Fraunhofer diffraction. So if we consider Fraunhofer diffraction, through a circular aperture, the result of this actually, I mean, so it starts off looking horrible, but then becomes really pretty straightforward. The idea is that you have some circular aperture and you've got light coming in to the aperture. You can describe this aperture by a radius r and an angle theta with x and y. And then essentially what you want to know is that distance down to your screen, x and y. Can you define an angle alpha in which you would expect to see, say, destructive interference right, where you would expect to see the dark patterns. And if you think about the shape of some of these Bessel functions, in particular the J0 Bessel function, right, without actually trying to think precisely of what it looks like, right, you know that it's oscillatory but non-periodic, it begins to look like the intensity pattern for a diffraction image, right, through an aperture. So it automatically sort of fits the geometry of the problem. The question is, how can we use this apparently weird and complicated function that comes from actually not, this abstract differential equation to solve a very simple question? What does the diffraction pattern look like when light comes through a circular aperture? You can show that the amplitude of the diffractive wave, which we'll call phi, is essentially the integral from 0 to a and the integral from 0 to 2 pi of e to the I b r cosine theta d theta r dr. Where the br cosine theta is essentially an expression of the phase of the diffracted wave. Okay, so in order to find then the amplitude as at any particular point, we need to be able to do this integral. B itself is given, depends on the wavelength. It's basically the wave number times sine of that alpha. Right, so whatever this amplitude is depends on that angle, which we could, of course, relate to x and y. It's a circular pattern, so it doesn't really matter on the screen at a particular distance. But generally, we look at these alphas. But given what we just did in equation d.3, we've now set up essentially an integral that we can solve by looking at that integral and replacing it with j naught. Right? So now we have phi is basically 2 pi times the integral from 0 to a times j naught as a function of br r dr. Oops, did that twice. In other words, the argument for the Bessel function of the first kind is b times r. Right? Now, this alone doesn't really get us much, but this is the reason why we went through some of those recurrence relations last time. So we know that not only that, but there are different relationships. So for example, x to the n times j sub n of x is equal to the integral of x to the n jn minus 1 of x dx. This may in fact be the reverse of the one that I talked about last time. I think I might have represented it as the derivative, but they're both the same. In other words, you can go either this way or that way, right? So given that, we can write that the amplitude of the diffracted wave is 2 pi over b times the integral of j now 1 minus 1 b of r b of r b dr as we do our substitutions, or I did this right, 2 pi over b squared times ab j1 of ab. Again, just going through all of these substitutions, the wave number 2 pi over lambda times a sine alpha times j1 of 2 pi a over lambda sine alpha. Okay, so that's the solution to this problem for a given aperture, right? But what we really, so that's the amplitude. We don't measure the amplitude, right? We measure the intensity. And how's the intensity related to the amplitude for a wave, an electromagnetic wave?
Square.
Yep. So we want the square. So the intensity is phi squared. So in this case, it's 4 pi squared over lambda squared times J1 of 2 pi a over lambda times sine alpha squared over sine squared alpha. That basically means that our intensity is equal to J1 squared times all of that argument over sine squared alpha. And that describes in essence, the intensity pattern for the diffraction. But what we want, what's useful, all right, so I mean, we could do this and we could plot this out, but often what's useful is asking, where are the zeros? Where are the dark fringes? Well, those dark fringes occur for zeros, right? So the zeros, often we have to look up, unless you start memorizing this, and I would recommend not, unless you want to impress people at parties. It's one thing to memorize pi to 10,000 places, but if you memorize J naughts zeros to 10,000 places, I'll be impressed. So J naught equals 0, as I said before, as a function of x, at x equals 2.4, 5.5, 8.7, so on. J1 equals 0 at x equals roughly 3.8, 7.0, 10.2, and so on. So you can build up this. Now, of course, given our solution, we want the zeros for J1, right? And if we ask what's the first, so the first dark line or the dark fringe, we want the first zero for J1. So in that case, it's 2 pi a over lambda times sine alpha. That's the argument of J1 equals the value of x in which J1 first goes to 0, and that's, say, 3.8317. That means that sine alpha is equal to 3.8317 over 2 pi a times lambda. And if you think about it, without putting anything into the equation that makes sense, sine alpha is proportional to the wavelength and inversely proportional to the aperture. For typical values, say for lambda in the green, say 550 nanometers, and say alpha is equal to 5 millimeters, then alpha that's small enough, let's say that's alpha is basically equal to sine alpha, and that gives you 6.10 to the minus 5, or about 14 arc seconds. Okay. So what's the point here? The point is that once we have our Bessel functions, often what's the most useful for our Bessel functions is finding out which zeros are appropriate for a problem, and then relating it back to relevant physical properties of the problem. Okay? Are there any questions? And if you look in your book, there are some other examples. I don't really have time to go over, but you can use this too for, and we'll kind of look at this in the example that you're going to break out for. Vibrating membranes, you can use this for resonant cavities. All of this depends on those, the function that you're looking at and the boundary conditions. So in this case, we didn't really have any boundary conditions. We were looking for zeros. In the case that you're going to do, we're going to look at one type of boundary condition. In the problem you do in the homework, you're going to look at another. We're going to deal with the Dirichlet boundary condition in a minute. In the homework, you're going to deal with Neumann boundary condition. That is, in the last problem, you're going to look at the derivative of the wave function, the standing wave, at the boundary is equal to 0. And in fact, the Bessel functions, including the spherical Bessel functions, have tables of zeros for their derivatives as well as for the functions themselves. Okay, so real quick in-class problem to nail this home. And I've gimmicked this up. Okay, so this isn't exactly perfect, but the point, I hope, is what gets across. So basically what we're going to consider is a standing wave. Oops. In a semi-infinite cylindrical cavity. In other words, this is a physics of music problem, right? We want to see what are the nodes and the antinodes of something in a pipe, okay? So what we would need to do then is solve for the wave equation in cylindrical coordinates. And what we can do is write that out as, so this is wave equation in cylindrical coordinates. And the semi-infinite part of it just means even though we're going to ignore much of what happens in terms of the z solution, it does mean that the function can't be infinite at r equals 0. Okay. So what this gives us is, if we focus on the radial equation, rho d rho of rho d p, we're in cylindrical coordinates, d rho minus m squared p is equal to 0 is our radial, after we do our separation of variables, is our radial equation. And this has a solution, p sub m is, let's see, equal to, the general case would be a sub n, j sub m, k, oops, rho, plus b sub m, n sub m, k, rho. So j is the Bessel function of the first kind. N is the Neumann function, Bessel function of the second kind. And here, k is basically z over r. Okay. So what I'm asking you to do is, given this expression, I want you to, in your groups, find the first antinode, that is the first 0, not including the origin, for the first 3 modes in this pipe, assuming that it follows the wave equation cylindrical coordinates. And we're not quite ignoring what's going on in the azimuthal direction. That's why we have that right there. But we are focusing on the radial solution. So we're focusing on this. And right. So let's see if I've got everything you need here. Got this, and we know that right. Yep, I think that's all you need. Are there any questions?
Does M start at 0 or?
So M starts at 1.
Okay.
Okay. All right, let me get you into your breakout rooms. Let's see, how many do we have here? Okay. No, wrong. No. Let's see, add a room. Try this again. Let's see. There we go. Okay. There you go. Do you have a question? Oh,
Is my audio working now?
yes, it is.
Yay, okay. Yeah, my audio wasn't working, and so I was gonna try to restart Zoom, but
Oh,
now it works. Okay.
all right. So join a breakout room. There you go. Hi, K equals 1 over R.
All right,
I don't know
cool.
if you
That
saw
makes
that.
sense.
Okay.
Yeah.
Okay, all right. Thank you. Let me get out of here.
Second one, your question. J1 in the back.
But yeah.
Oh,
Hi.
typo, K equals 1 over R.
Got it. Thanks.
Yeah, all right. There you go. Hello.
Hey.
If you didn't see it, there was a typo. K equals 1 over R. Makes it a little
Alrighty.
more, yeah.
Okay, I was wondering what we were doing with that
Yeah,
Z
okay.
dependence.
Yep. All right. Hey guys, I don't know if you saw, but there's a bit of a typo. K is equal to 1 over R. Hopefully that makes sense. Okay. Sorry. Hey guys,
Hello.
how's everything going?
Good.
Pretty good.
One more week.
Yep. So close.
Mm-hmm. Do you have any big projects or anything like, or papers or anything like that left to go?
I have my math capstone write up
Mm.
and a paper for food ethics.
Food
Which-
ethics?
Yeah. The second one shouldn't be too bad.
No. So what department is that in?
Philosophy.
Oh, okay.
That's my second major.
Okay.
Because it was interesting and also good for the GPA. So
Old move, Cotton.
yeah. Well, it's a double win because it only makes your GPA look not as bad if you have two majors, but it's also the only major that'll raise your GPA by taking it, or at least for me. So I was already doing math, and it was kind of like in terms of like how to think, it's a very easy transition.
Mm-hmm. How about you, Nick? What do you got going?
We just had paper for lab
Mm-hmm.
electronics. And then we're actually making a video for our last project.
Oh, really?
Instead of a PowerPoint or a talk or whatever.
Okay.
Which became interesting. Actually got these cool.
Oh, I saw those. Is that those
Yeah.
are the muon detectors?
Yeah, they're pretty cool.
Yeah. I think we're going to be doing a lot more stuff like that in the fall, where we're sending out stuff to Makerspace to create stuff for people. I was on campus for the first time in weeks 2 days ago, measuring 6-foot spaces in 121, which was horrifying because you can only fit 40 people in that room if they're 6 feet apart. And you can imagine that it gets worse in the lab or 115. I think we can fit 12 people in there 6 feet apart. So.
Yay, smaller class sizes.
Yeah, I'm sure that we will be completely compensated for teaching twice too. I should probably not say this while I'm being taken. I have to edit this in post. Okay, I apologize. This was I threw this together, was working on this last minute, and then I had a phone call from an advisee. So, I mean, basically the idea here, and I'll write this up in a little more detail, is that the Neumann functions blow up at the origin, so you can't use them. So you're left with the Bessel functions, and to find those antinodes, you have to find the first zeros of m equals 1, 2, and 3. And that's all there is to it. And that's essentially how you use these equations and why the zeros are important. And you'll notice on that table as well that you can find the zeros for the derivatives in addition to the functions themselves. Okay, so that makes sense? Thumbs up, makes sense? Yeah, okay, yes, no? Okay. Let's finish this off with spherical Bessel functions. And I realize I'm kind of skipping over a whole bunch. So as I mentioned before, there are the Hankel functions and the modified and all of these things. They're basically Bessel functions that have imaginary arguments or linear combinations of j sub n and n sub n. Sometimes you'll see y sub n instead of n sub n. But basically you get the spherical Bessel functions. by looking, okay, let me look at this. A solution for the heat equation or Helmholtz equation in spherical coordinates and isolating the radial component. So if you focus on r squared, d squared r, dr squared plus 2r dr plus k squared r squared minus, and if you remember, and then sometimes we've called this L plus or L times L plus 1. We'll use n times n plus 1 times r is set equal to 0. And I'm going to skip over how we can bend this. This is self-adjoint, but not the Bessel equation itself. But we can manipulate this, and essentially the manipulation that you can go through and the book goes through is to redefine R in terms of another variable that essentially gets back to our Z dependence. Namely, we're going to, well, call it Z. We'll set R as a function of K little r equal to some function Z as a function of K over R divided by K over R square root. And then pull that through this differential equation. And there's a bunch of algebra, but where we end up is the function r squared d squared z dr squared plus r dz dr plus k squared r squared minus, this is an r, minus, interestingly, n plus 1/2 squared times z is equal to 0. Okay, so I realize I'm skipping 8 lines of algebra to do this, but you can do it. So it's similar to, I mean, it looks like the Bessel equation. The difference here, and this is for the Bessel function of the first kind, essentially. The difference here is we have now non-integer indices. Right? So the definitions for these spherical Bessel functions, we use lowercase with the same letter to represent it. So little j sub n of x is equal to, with the appropriate normalization, pi over 2x times the Bessel function that we're familiar with, but now n, where the index is n plus 1/2 times x. And we can do the same thing for the Neumann functions, the same normalization, because this is essentially the same equation, times that. And similarly, we can do the same thing for the Hankel equations, which are the modified Bessel functions, but now in for spherical coordinates. Right. So yeah, so now all we've been doing for the last couple of weeks, really, if you think about it, 3 weeks, is looking at how do we solve these partial differential equations of increasing complexity and interesting geometry, right? It's one thing to do things in Cartesian coordinates. It's another thing entirely to do it in other coordinates. But then the question is, what are we after, right, intuitively? One thing we're always after for is the wave function, if we're talking about quantum, where this often comes up. And that's useful because it contains all the information about the state of a system. But oftentimes we're interested in very specific numbers. We're interested in the eigenvalue, the eigenfunction, or we're interested in in the case of these functions, where they go to 0 because that contains information itself. So, in a hugely important example of why we can use this, let's go back to a very basic question that is particle in a sphere. And ultimately, can we ask, what's the minimum energy for a particle in a sphere using Schrodinger's equation? Okay, so that means we need to solve minus h bar squared over 2m del squared psi is equal to psi, where psi for r less than a is finite, and psi of a, or at r equals a, is equal to 0. Right? In other words, we can't, we're basically confining it to this sphere. Right? It's an infinite, it's like putting it in a box, right? But we're putting it in a sphere. And we already know what the answer is, or if we don't, we can look it up, right? Because you've seen this before. So what we want to find is, what is the minimum energy for a particle that's located somewhere in this sphere? So in order to do that, we would need to solve this in spherical coordinates. So that would be d squared r, dr squared plus 2 over r, dr plus k squared minus n times n plus 1 over r squared r set equal to 0, with k squared bringing in all of the normalization from the problem, that is 2me over h bar squared. So we've done this before, and you've done this before in several other classes. We want the lowest energy. So we know that we're dealing with n equals 0, right? And we know from this problem itself that this is going to be a linear combination of the spherical problem of the spherical Bessel function and Neumann function, namely the solution, not unlike what we started with in the in-class problem. R is going to be some constant times the spherical Bessel function J0 of Kr plus B in 0 of Kr. Right? That's the general solution. But what do we know, or what do you suspect is true? If the Neumann function and the spherical Neumann function is essentially like the regular Neumann function.
It'll blow up at the origin.
Right. So this has to be 0. Actually, B has to be equal to 0. Right. So we have that this is entirely due to this, or solved by the spherical Bessel functions. And since we've chosen n equals 0, we know that there's no orbital angular momentum. And so that requires k times a is equal to the square root of 2me over h bar a equals alpha, where alpha is a 0 of j naught. So all we have to do to solve this problem then is find the first 0 for the spherical Bessel function. And it turns out that the first, if you look at the table, again, this is dependent on tables, the first 0, oops, that's a weird 0, for j naught is pi, happily enough. So that means that E min in this case is pi squared h bar squared over 2ma squared equals h bar squared over 8ma squared, right? Which is what you would expect and is something that you've seen in quantum. Okay, so I'm out of time, but I hope that and I know that this is kind of rushed. It's kind of rushed because of circumstances. I knew that this was going to happen as we were starting this term with losing a week as we did. But I wanted to give you enough of a taste of the Bessel functions so you can see their utility and see that their utility isn't so much the actual form, but what we can do with when the functions or the derivatives of the functions go to 0. What does that tell us about the physical nature of the system? Okay. Any questions before we go?
I have a quick question. Hopefully it's quick. For the generating function,
Yes.
does that come from like knowing that it works, kind of like an integrating factor from
Yes.
back when? Okay.
If you look, actually, in fact, it's very, I mean, either cutely or annoyingly said in the homework problem I assigned. There's a homework problem that takes you through the step of the generating function to bring it out of the realm of magic.
Yeah, that felt weird because they have you use a recurrence relation to find the generating function, but they found the recurrence relation using the generating function.
I know. I know. They're adorable that way. Yes. Okay, so the other thing I'd like you to do is to not forget to please, just 1 or 2 sentences, do a reflection today. And then I'll be around for questions on the homework, which is due tomorrow. If you have any problems with that due date, please contact me. But just realize that we're crushing up against, we got one more problem set, and then we've got the final. Okay? All right. Bye. See you later.
Thank you. Bye, Rick.
Thank you.